Hey everyone. So, we are talking about calorimetry, which we talked about last year, so this should be pretty much review for us. But let's go over it just to make sure. So, calorimetry, which all calorimetry is, that C has got to be annoying. That calorimetry, all it is that it measures heat flow. So, like, how easy is heat to flow through water? How easy is it for heat to flow through a metal? How easy or hard is it to heat it up? Okay, and last year we used an equation called Q-SMAT. Okay, Q-SMAT, Q-MCAT, they're all the same thing. So what I just said there was Q-MCAT. You might see something like this instead. Okay, the only difference being the S and the C, right? This is mass, change in temperature. S and C, this is just heat capacity, and this is specific heat. You can use them interchangeably, it doesn't really matter. But we use Q-SMAT, because that's what the cool kids do, is use Q-SMAT. So what is Q? Q is just heat or energy in joules. That's what we're trying to find out for the most part. Delta T, right? You know, delta is change. Delta T is change in temp or temperature. Okay. This could be in Kelvin or Celsius because they change from the same ratio. M is mass, which is in grams. Okay, so make sure your mass is in grams. And then S is specific heat. Specific heat, which is joules per grams degrees Celsius. And I just want to talk about specific heat for a little bit. It's just how easy it is to heat something up. Something that has a specific heat of 1 joule per gram degree Celsius means it takes 1 joule of energy to heat up a gram of that substance 1 degree Celsius. So the lower the specific heat, the easier it is to heat up, right? With that 1 joule per gram degree Celsius, it only takes 1 joule. But if I said 10 joules per gram degree Celsius, you'd have to put 10 joules of energy to just raise 1 gram of substance by 1 degree Celsius. Okay, so be aware of that. Things like metals have really low specific heats because they're easy to heat up. Those atoms are easier to excite. But things like water have a specific heat of 4.184, so that takes a little bit more energy to heat up the water. Case in point, right, when you're heating up boiling water, when you're boiling water, the water takes a long time to get hot, but that pan that it's in heats up real quick and can burn you, okay? So we're just going to do a couple of questions here, and then that'll be it for calorimetry. So again, we're using Q-SMAT. Let's do an example. Okay, how much energy is needed to change the temp of water, or to change the temp of 50 grams of water by 15 degrees Celsius. Okay, and the specific heat of water, I don't expect them to have you memorize it. They usually give it to you, but if you don't know it, the specific heat of water, which they will put as S sub H2O, is 4.184 joules per grams degrees Celsius. Okay. So all this is that we have a Q-SMAT problem here. When you see specific heat, you're automatically thinking Q-SMAT. Q is the heat that we're looking for, or how much energy, so we're good. That's what we're looking for. So now we should just plug and chug. Specific heat of water is 4.184 joules per grams degree Celsius. M is mass, which is 50 grams. And delta T is change in temperature, which is 15 degrees Celsius in this case. There wasn't a final or initial that we had to separate. We multiply those together and our heat should end up being 3,135 joules, right? And that heat is positive. That means heat was put into the water, right? If it was negative, that means heat would be released. But in this case, heat is being put into the water. Let's do one more example, and then one more tricky example, and then I'm done with this for the most part. Actually, two more examples. Sorry. I forgot I got one more concept to go over. So, example. What is the final temp after 840 joules is absorbed by 10 grams of water at 25 degrees Celsius? So here, it wants a final temp after we put 840 joules and 10 grams of water at 25 degrees Celsius. Okay, here you're thinking, oh man, okay, I see joules, I see mass, and I see temperature. And water, I know the specific heat of that, so let's go ahead and think QSMAT, right? If I wasn't talking about this just a couple seconds ago, you might be confused on what equation to use, but here we're going to use QSMAT. I know my heat is 840 and it was absorbed, so it's positive, right? If it was released, it'd be negative, but it's absorbed, so it's positive. Specific heat, since we're dealing with water, is 4.184 joules per gram degree Celsius. Mass is 10 grams. And change in temperature, right? We want the final temperature. Well, remember, change in anything is final minus initial. So temperature is temperature final minus initial, which is 25 degrees Celsius. Okay? So, here we go. Now it's just a little bit of algebra to help us solve this. Let's go ahead and get everything by itself that we can. So it looks like we can get TF minus 25 degrees Celsius by itself. So let's divide by 4.184 and 10 on both sides. Okay, 840 divided by 4.184 times 10 equals, I got 20.076 equals TF minus 25, right? And then to get TF by itself, you just add 25 to both sides. And our final temperature will be pretty much 45.1, right? If I were to round, 45.076 degrees Celsius. Okay? So that is a little bit of a tricky one, but it's not too bad. Let's go on to our next example. So here is the hardest type of problem that you'll see that the AP likes to throw at you, because it's something that we will actually do in lab, or that actually happens in lab. So here the question reads, a piece of metal weighing 59 grams has been heated to 100 degrees Celsius and then put into 100 milliliters of water. The temperature initial of that water, 23.7 degrees Celsius. The metal and water reach 27.8 degrees Celsius. Assuming no heat loss, calculate the specific heat of the metal. Okay, so what's happening here is that we have two different substances transferring heat. Okay, we're having a hot metal transferring heat to a colder liquid. So what we do here is we do two QSMAT equations. And we're going to go ahead and set Q hot equal to Q cold. Okay, so So this is Q hot equal to Q cold. But one of those has to be negative because one of them is releasing heat and one of them is absorbing heat. We're saying no heat loss is happening. So something has to happen where one of them's releasing heat and one of them's absorbing heat. Well, which one's going to be releasing heat? The hot one, right? It's going to have a bunch of energy ready to transfer to water. So all this is a negative Q hot equals positive Q cold type of reaction. So let's go ahead and let's set it up on the bottom, and then I'll erase this top part and we'll get going. Actually, I could probably do it right here. No, I'm going to do it over here. Sorry for wasting your time. Anyway, negative Q hot, right? SMAT, SMAT. So we know that for the Q hot, the metal or the specific heat is what we're looking for, right? The metal was 59 grams. Okay. Change in temperature. Temperature final, we know, was 27.8. And we know temperature initial of the metal was 100. So that takes care of our hot side. Negative S equals mass times change in temperature. Equal to Q of the cold, right? SMAT of the cold. Water, we know the specific heat is 4.184 joules per grams degrees Celsius. We know the mass of water was 100 milliliters. Well, that just means 100 grams, right? Because the density of water is 1. And delta T, we know the final temperature of the water. Again, it equilibralized at 27.8 for final, and its initial was 23.7. Okay? So again, we are just going to do a little bit of algebra here, and I'm going to get S by itself. So I'm going to divide by negative 59 grams. You could simplify that if you want to, right? So these will all cancel out. If I do it to one side, I got to do it to the other. So negative 59 times 27.8 minus 100. So everything cancels out except for specific heat of the metal. And you'll notice that this negative and this negative will cancel out and your answer will be positive, so you know you're on the right track. Okay? We simplify what we can. We plug this into our calculator, and our specific heat of the metal should be 0.402 joules per grams degrees Celsius. Okay. Then we could go ahead and we could go online, look up specific heat of known metals, and then we could identify that metal. So that is calorimetry, guys. That's as difficult as it will get. Get you some practice. Have yourself a good day.